The Mariana Trench is located in the western Pacific Ocean, in an area that appears on a map as a vast, empty expanse of water between Asia and Australia. From the surface, it looks like an ordinary ocean. Waves, a horizon, the occasional ship, and the occasional tropical storm. Nothing about this place suggests that directly beneath the surface lies the deepest point on the entire planet. The basin extends in an arc for approximately 2,500 kilometers. If you imagine this distance on land, it would be comparable to the length of Europe from Spain to Poland. This is not a narrow fissure, but an entire tectonic system with varying depths, complex topography, scarps, and internal depressions. The average width of the basin is about 60 to 70 kilometers, but in some places it widens or narrows. The deepest point is located in the southern part of this arc. It's called Challenger Deep. According to modern measurements, the depth here reaches approximately 10,900 to 11,000 meters. These figures are being refined as technology advances, but the order of magnitude remains unchanged, almost 11 kilometers. To understand scale, it's important to imagine the vertical dimension. We're used to thinking horizontally, the distance between cities, the length of rivers, the length of roads. But the Mariana Trench is primarily vertical, almost 11 kilometers down. Everest is 8,848 meters high. If you were to lower it to the bottom of the valley, there would still be more than 2 kilometers of water above its summit. This means that the highest point on land would not reach the ocean surface if it were located in this valley. Another example is commercial airliners. Most of them fly at an altitude of about 10 to 11 kilometers. This is roughly the same scale, but directed upward. This means the depth of the depression is comparable to the aircraft's altitude. However, the numbers alone don't provide a complete understanding. More importantly, realize that nearly 11 kilometers of water is a colossal mass. Water is heavy. 1 cubic meter weighs about a ton. There are approximately 11 kilometers of this mass above the bottom of the depression. The Mariana Trench is located adjacent to the Mariana Islands, a chain of volcanic islands that stretches in an arc. These islands are the visible part of the same tectonic system. Their existence is directly linked to processes occurring beneath the trench. When looking at bathymetric maps of the ocean depths, the trench appears as a dark, curved band. The color gradually darkens as the depth increases. The deepest point is located at the center of this arc. It's important to understand that the basin isn't a smooth bowl. Its topography is complex. The slopes are steep, almost vertical in places. There are steps, and there are more gentle sections. Within, there are additional depressions. It's not a single pit, but a system of deep structures. The Mariana Trench is part of the so-called Pacific Ring of Fire, a zone of heightened seismic and volcanic activity surrounding the Pacific Ocean. Earthquakes in this region occur regularly, driven by the movement of lithospheric plates. When viewed cross-sectionally across the Earth, a trench is a place where one section of the oceanic crust literally drops away, creating extreme depth. Interestingly, despite its fame, the Mariana Trench has been explored far less than the surface of the Moon or Mars. The reason is simple. Its depth creates technical challenges. Exploring its bottom requires sophisticated equipment capable of withstanding extreme pressure. Another important aspect is its isolation. The basin is located far from any major continent. It's not a tourist destination, nor is it located near shipping routes. Much of the surface above it appears empty. This is why it long remained a near mythical point on the map. Many people imagine it as a bottomless pit. In reality, its depth is finite and measurable, but the feeling of bottomlessness stems from the fact that almost no one has ever seen it in its entirety. We know it from instrument data, fragmentary footage, and scientific reports. On a global scale, the Mariana Trench is just a thin line, but vertically it's the most extreme point on Earth's surface, and that's just the geography. True understanding begins when we consider how and why it came into being in the first place. To understand the origin of the Mariana Trench, we need to forget about water for a moment. Imagine the Earth without oceans, as a sphere whose surface consists of large plates tightly pressed against one another. These plates are not firmly anchored. They slowly move across the flexible mantle, like vast ice fields on the surface of a slow-moving current. Lithospheric plates move at a rate of just a few centimeters per year. This is roughly the speed at which fingernails grow. On a human scale, this is practically motionless, but on a time scale of millions of years, such movements change the shape of continents and ocean floors. In the Mariana Trench, two oceanic plates, the Pacific and Philippine, collide. The Pacific plate is older and denser here. When the two plates meet, the denser one begins to subduct beneath the lighter one. This process is called subduction. Subduction is not a collapse or a fault in the traditional sense. It is a slow, continuous descent of one part of the Earth's crust beneath another. The edge of the Pacific plate bends and begins to sink downward into the hotter, more ductile layers of the mantle. When a plate flexes, a long, deep trench forms on the surface. The Mariana Trench is precisely such a trench. If you imagine the edge of a slab in cross-section, it resembles a sheet of cardboard that is slowly bent downward. A depression forms at the bend. Over time, this depression becomes deeper. It's important to understand that the depression isn't dug out by water. It's formed by the movement of the Earth's crust itself. The water merely fills this depression. When the Pacific plate subducts beneath the Philippine plate, it extends tens and hundreds of kilometers. As it subducts, the plate heats up and partially melts. This triggers magmatic processes and leads to the formation of the volcanic arc known as the Mariana Islands. Thus, the basin and the islands are part of the same mechanism. Subduction is accompanied by earthquakes. Stress builds up and is then released. Therefore, the Mariana Trench region is considered a seismically active zone. However, the depth of the trench is not formed by a single strong event, but by constant, slow pressure and plate bending. Interestingly, oceanic crust ages as it moves away from mid-ocean ridges. The Pacific plate near the Mariana Trench is one of the oldest and densest. This is why it sinks beneath another plate. Over time, the edge of the subducting plate becomes steeper. Pressure from above intensifies the bending. Millions of years of such processes lead to the formation of extreme depths. Subduction zones exist elsewhere on the planet, but the depth of the Mariana Trench is explained by a combination of factors: the age and density of the plate, the speed of movement, and the geometry of the collision. As a result, the bending is particularly pronounced. When viewed in cross-section, the basin resembles a narrow and deep V-shaped structure. The slopes are steep, almost vertical in places. The bottom is relatively narrow compared to the overall length of the system. The process continues today. The plate hasn't stopped moving. Earthquakes occur every few years, recorded by seismologists. Geological time passes slowly, but inevitably. Perhaps in millions of years, the depth will change. The plate may subduct further, or the processes may be redistributed. But on a human scale, the Mariana Trench remains a stable structure. Another interesting point concerns sedimentation. Despite its extreme depth, the basin gradually fills with particles falling from above. Marine snow, volcanic ash, and microscopic remains of organisms, all of this slowly accumulates on the bottom. If plate movement had stopped, the trench would have become shallower over time. But subduction continues to maintain its shape. Thus, the Mariana Trench is not a hole in the earth, but the result of enormous and very slow geological forces. It exists thanks to the movement of the lithosphere, which has been ongoing for tens of millions of years. This realization gives depth a special dimension. It's not just an extreme point on a map, but a place where you can see the planet literally changing its shape. When talking about the Mariana Trench, one number often comes to mind: almost 11 kilometers. But depth itself is just a distance. The real significance begins when you realize that those kilometers are filled with water. Water is a heavy medium. 1 cubic meter of seawater weighs approximately 1 ton. This means that for every square meter of surface area at a depth of 11 kilometers, a column of water weighing thousands of tons presses down. But it's easier to think in terms of pressure. On the Earth's surface, we live under the pressure of 1 atmosphere. We don't feel it because our bodies have adapted to it. At a depth of 10 meters, the pressure increases by approximately 1 atmosphere. This means that at a depth of 100 meters, the pressure is already about 10 atmospheres. At a kilometer, it's about 100 atmospheres. And at a depth of almost 11 kilometers, the pressure exceeds 1,000 atmospheres. This means that a force of over a ton acts on every square centimeter. If you placed an object the size of a postage stamp on your palm, at the depths of the Challenger Deep, that area would be pressed by a mass comparable to a passenger car. The human body is unable to withstand such conditions. Any cavity filled with air would instantly collapse. The lungs, sinuses, even microscopic gas bubbles in tissue. All of this makes the body vulnerable. This is why deep-sea diving is only possible inside sealed apparatus. From a physical perspective, water compresses less than air, but at this pressure, even it becomes denser. At a depth of almost 11 kilometers, water density is higher than at the surface. This means that the physical properties of the environment change. The temperature at the bottom of the trench remains around 1 to 2 degrees Celsius. This is almost the freezing point of seawater. The combination of cold and pressure creates conditions in which most familiar materials begin to behave differently. Metal, for example, can deform under pressure. Even strong steel experiences stress close to its breaking point. This is why deep-sea submersibles are spherical. A sphere distributes pressure evenly across the entire surface. Flat walls or corners would become vulnerable points. The walls of the bathyscaphe Trieste, which sank to the bottom in 1960, were about 13 centimeters thick. Even so, the crew heard clicking sounds in the hull during its descent. This was the sound of the metal adjusting to the increasing load. Modern devices use titanium alloys or composite materials. They are designed to eliminate any internal voids. Windows are made of special transparent materials that can withstand enormous pressure. Every bolt and every weld undergoes meticulous testing. But pressure affects more than just technique. It determines the very structure of life at depth. Deep-sea organisms lack gas cavities. They lack the swim bladder found in many fish in higher layers of the ocean. Gas under such pressure would be a critical vulnerability. Their bodies are soft, flexible, almost gelatinous. This is no accident. It's an adaptation to the environment. Movement speed at such depths is slow. Energy is distributed economically. High pressure slows chemical reactions. Metabolism in deep-sea organisms is slower. Interestingly, even sound behaves differently at depth. Water conducts sound better than air, but at greater depths, acoustic conditions change. However, the human ear will hear nothing there. Without the medium of air, sound is not perceived in the usual way. Inside the apparatus, silence reigns, interrupted only by the hum of the life support systems. Another aspect is light. At a depth of about 1,000 meters, light disappears completely. Not a single ray of sunlight reaches the bottom of the Mariana Trench. This means absolute darkness, lasting for millions of years. If you imagine diving, the water remains blue for the first few hundred meters. Then it darkens. Then it becomes deep blue. Then black. And then the color doesn't change anymore. Depth is sensed not through sight, but through instruments. The sheer scale of the water comes gradually. 11 kilometers of water isn't just a distance. It's a tremendous weight, cold, darkness, and isolation. From a physics perspective, the Mariana Trench is an extreme laboratory. Here one can study how materials behave under pressure, how the properties of liquids change, and how biochemistry adapts to the environment. But for a person, the most powerful sensation is the realization that you are at the farthest point from the Earth's surface. Below there is no land, no mountains, no buildings, only a slowly moving lithospheric plate beneath a layer of sediment. And it was precisely in these conditions that rare historical dives took place, which are worth telling in more detail. In January 1960, a U.S. Navy research vessel was in the western Pacific Ocean. On board was an unusual vehicle named Trieste. It was a bathyscaphe designed by Swiss engineer Auguste Piccard and later acquired by the U.S. Navy for deep-sea exploration. The Trieste was unlike modern submarines. It consisted of two main sections. The upper section contained a large float filled with gasoline. Gasoline is lighter than water and does not compress as much under pressure, so it provided buoyancy. Below the float was a small spherical cabin. This is where the crew resided. The sphere was made of steel approximately 12 to 13 centimeters thick. Its internal diameter was just over 2 meters. It was cramped inside, with almost no room for movement. On January 23, 1960, 2 people were inside the sphere: Jacques Piccard, the son of the spacecraft's creator, and U.S. Navy Lieutenant Don Walsh. Preparations for the dive took months. Calculations were verified, structures were reinforced, and life support systems were tested. No one had ever dived to such a depth before. Theoretically, calculations showed the hull would withstand the pressure, but real-world experience was lacking. In the morning, the bathyscaphe began to be lowered into the water. After checking its systems, it began a slow descent. The descent was gradual. Ballast supported the apparatus and could be jettisoned as needed for ascent. The first few hundred meters were no different from a typical deep-sea dive. Light penetrated the water, and the temperature gradually dropped. Then the water became darker. After a while, only blackness remained beyond the portholes. The descent lasted almost 5 hours. It was a long wait in a confined space. Inside the cabin, silence reigned, broken only by the occasional sounds of the equipment. As the depth increased, the pressure increased. At a depth of approximately 9 kilometers, a moment occurred that the crew remembered especially vividly. A loud cracking noise was heard. This was caused by the destruction of the outer acrylic glass of one of the auxiliary windows in the float. The main cabin remained sealed, but the sound revealed just how extreme the conditions were. Despite this episode, the descent continued. When the bathyscaphe reached the bottom, the instruments showed a record depth, approximately 10,916 meters by the measurements of the time. The apparatus touched the surface gently. A cloud of silt rose up, temporarily obscuring the view. The time spent on the bottom was limited, about 20 minutes. Visibility remained poor due to the disturbed sediment. Pickard later wrote that in the spotlight's light, he saw something resembling a flatfish. Later, scientists doubted this observation, suggesting it might have been another organism. But the very fact of life at such a depth already seemed incredible. After a short stay on the bottom, the ballast was released and the ascent began. It took approximately 3 hours. When the Trieste surfaced, it was a historic event. For the first time, humans had reached the deepest point of the ocean. This descent was more than just a technical achievement. It became a symbol of the limits of possibility. At a time when humanity was just beginning to actively explore space, 2 men reached the deepest point on Earth. Interestingly, no one repeated this achievement for over 50 years after 1960. The reason was not a lack of interest, but the complexity and cost of such expeditions. Vehicles of this class require enormous resources. The Trieste dive remains one of the most daring experiments in the history of oceanography. 2 men voluntarily descended into an environment where pressure exceeds 1,000 atmospheres, relying on calculations and the strength of metal. This moment became the starting point for all subsequent exploration of the depths. After the Trieste dive in 1960, there was a long pause. Humanity had ventured into space, landed on the moon, and sent probes to other planets. But no one had returned to the deepest point on Earth for over 50 years. Technically possible, it was extremely difficult and expensive. The depths required not just a robust craft, but a completely different design approach. Interest in the Mariana Trench revived at the beginning of the 21st century. One of those who decided to repeat the dive was director James Cameron. He was attracted not only by the record depth, but also by the idea of descending to the least explored part of the planet. Cameron had been interested in oceanography for many years and had participated in expeditions to the sunken Titanic. But the Mariana Trench presented a whole new level of complexity. Deep-sea submersible was created for diving. Challenger. Unlike the Trieste, which was a large float with a suspended sphere, the new craft was compact and vertically oriented. It was approximately 7 meters long, but the pilot's cabin was located at the bottom and shaped like a small sphere with a diameter of just over a meter. The apparatus was constructed from modern materials, including specialized composites and synthetic foams capable of withstanding extreme pressure. The life support, navigation, and video systems were significantly different from mid-20th century technology. The cameras allowed for high-resolution filming, capturing the smallest details. On March 26, 2012, Cameron began his descent. The dive took about 2.5 hours, significantly faster than the Trieste. Modern technology allowed for the process to be optimized. As the submersible descended, the water darkened, and instruments recorded increasing pressure. At a depth of approximately 10,900 meters, the submersible reached the bottom. Unlike the 1960 crew, Cameron spent nearly 3 hours at the bottom. He collected sediment samples, recorded video, and observed the surrounding environment. According to him, the bottom appeared as a flat plain with occasional depressions. The spotlights revealed fine details in the darkness: sediment particles, traces of organisms moving about. Interestingly, Cameron described the feeling of isolation as something quite special. At this depth, there's no sense of space in the conventional sense. All around is absolute darkness. Nothing visible exists beyond the spotlights. The knowledge that there are nearly 11 kilometers of water above you doesn't overwhelm you emotionally, but it creates a profound sense of scale. Cameron's dive sparked a new wave of interest in deep-sea exploration. Private projects and international expeditions emerged. New manned vehicles capable of reaching extreme depths were developed. One of the most famous programs was 5 Deeps Expedition, during which explorer Victor Vescovo made several dives to the Challenger Deep in 2019. His submersible limiting factor became the first deep-sea vehicle certified for multiple descents to maximum depth. This marked a significant step forward. Whereas such dives had previously been isolated events, regular expeditions were now possible. Modern devices are equipped with robotic arms, water chemistry sensors, and precision positioning systems. They can collect soil samples, record microorganisms, and measure the physical parameters of the environment. At the same time, autonomous underwater vehicles, AUVs, are being developed. They can operate longer than manned submarines and perform detailed mapping. Multi-beam echo sounders enable more accurate terrain maps. Despite technological advances, every dive remains a complex operation. The apparatus must be delivered to a remote area of the ocean. Weather plays a significant role. Strong waves can complicate the descent and ascent. All systems are checked repeatedly, as in the event of an accident, there is no help available. Recent expeditions have made it possible to determine the depth, study the bottom sediments, and collect biological samples. The existence of life at extreme depths has been confirmed, and new species of amphipods and microorganisms have been discovered. Interestingly, during some dives, traces of human activity, plastic bags and debris, were found on the seabed. This was an unexpected reminder that even the most remote point on the planet is not isolated from global processes. 21st century technology has made it possible to return to a place where only 2 people once descended. But despite all this progress, the Mariana Trench remains difficult to access. The number of people who have visited its bottom remains smaller than the number who have traveled into space. And each such descent is not only a scientific mission, but also a reminder of how deep and complex our planet is. When people talk about the deepest point on the planet, their imagination often conjures up dramatic images, cliffs, cracks, unimaginable shapes. In reality, the picture is much quieter and more tranquil. The bottom of Challenger Deep doesn't resemble a fantasy landscape. It's a relatively flat surface, covered with a layer of fine sediment. This sediment consists of material that has been slowly sinking from above for millions of years. Microscopic particles of dead organisms, plankton fragments, mineral dust, volcanic ash, all of this gradually settles to the depths. The process is very slow. A particle can take weeks or even months to sink through the water column. At the bottom, this material forms a soft silt. When the bathyscaphe Trieste touched the surface in 1960, a cloud of silt rose up, almost completely obscuring the view. This suggests that the sediment is loose and fine, easily disturbed by the slightest movement. Modern dives have confirmed that the seabed isn't completely flat. There are small depressions, traces of organism movement, and microscopic elevations. But overall, it's not a rocky abyss, but rather a deep sea plain. An interesting point concerns the sediment thickness. In some areas, the silt layer reaches tens of meters. Beneath this layer, the subducting tectonic plate continues. This means that not only biological, but also geological processes are occurring at the very bottom. Studies of bottom samples have shown that microorganisms are present in the sediments. They live not only on the surface of the silt, but also within it, at depths of several centimeters or even meters. These bacteria feed on organic matter and participate in the processing of matter. One of the unexpected results of modern expeditions is the discovery of microplastics in samples of benthic organisms. Plastic particles were found in the bodies of amphipods. This means that even the deepest point of the ocean is connected to the global waste circulation system. Plastic that enters the ocean gradually fragments and can sink to extreme depths. Traces of large impacts were also recorded on the seabed. For example, the remains of marine animals that descend from the surface. Such events create localized bursts of activity. Organisms congregate around a food source, and the area becomes more active for a while. Some studies have found evidence of chemical activity associated with tectonic processes. Although the Mariana Trench is not known for active hydrothermal vents at its deepest point, the chemical composition of the water and sediments indicates interaction with deep-seated rocks. Modern cameras have captured the movements of amphipods, small crustaceans, and even rare sightings of fish. These fish don't look intimidating. They are small, with soft bodies adapted to pressure. Their movements are smooth and economical. Another discovery is evidence of bioturbation, the mixing of sediments by living organisms. This means that even at a depth of almost 11 kilometers, the soil is being reworked by living organisms. The silt doesn't lie as a dead layer. It's slowly being transformed by life. It's also interesting that the water at this depth isn't completely still. Although there are no strong currents, slight horizontal movements are recorded. These influence the distribution of particles and the formation of microrelief. Scientists are also studying the chemical composition of the bottom water. Various minerals, ions, and gases are dissolved in it. At this pressure, the solubility of some substances differs from that at the surface. This creates unique conditions for microbial life. One area of research has become the study of the resistance of DNA and proteins to extreme pressure. Samples recovered from the depths are analyzed in laboratories around the world. This helps us understand the limits of biological resistance. The depression wasn't empty, nor was it fantastical. It was quiet, cold, and surprisingly stable. Life there exists not in the form of giant creatures, but in the form of small, slow-moving organisms adapted to the constant environment. Each dive adds new details to this picture, but even today, the floor of the Mariana Trench has been explored only fragmentarily. Its area is vast, and the number of actual observations is limited. It is precisely this limited knowledge that makes it both a concrete and mysterious place. Life at a depth of almost 11 kilometers is unlike life in the upper layers of the ocean. There are no coral reefs, no schools of fish, no diversity of vibrant forms. Everything is arranged differently. The environment is stable, cold, dark, and extremely dense. And it is precisely to these conditions that evolution has adapted the organisms that inhabit the Mariana Trench. Microorganisms form the foundation of the deep-sea ecosystem. These are bacteria and archaea that can survive under extreme pressure. They are called barophilic or piezophilic organisms, from the Greek word for pressure. The proteins in the cells of these microorganisms have a special structure that resists compression. Their cell membranes contain more unsaturated fatty acids, making them flexible and allowing them to maintain functionality under high pressure. These microbes process organic matter that settles on top and participate in biochemical cycles. Their activity is invisible to the naked eye, yet they form the basis of the food chain. The next level is small invertebrates. The most well-known of these are amphipods. These are crustaceans resembling amphipods but reaching larger sizes. Some specimens found at depths of over 10,000 meters reach several centimeters in length. The amphipod's body lacks gas cavities. Its tissues are soft and dense. Their bodies contain increased concentrations of molecules that stabilize proteins under pressure. They feed on organic debris and can actively move along the bottom, especially when a food source, for example, the body of a dead animal, descends to the depths. Isopods have also been found at extreme depths. Their movements are slow and their energy expenditure is minimal. In conditions where food supply is irregular, energy conservation becomes a key survival strategy. Scientists have been particularly interested in fish living in the Hadal zone, depths greater than 6,000 meters. The most well-known representatives are fish of the Liparidae family, sometimes called snailfish. They have soft, almost transparent bodies, devoid of hard, bony structures. Their skeletons are reduced, and their swim bladder is completely absent. These fish rarely exceed 30 centimeters in length. They swim slowly along the bottom or hover in the water, searching for small invertebrates. Their bodies are adapted to constant pressure. They have no cavities that could collapse. Interestingly, the limit of fish distribution is limited to depths of approximately 8,000 to 8,500 meters. Below this level, the pressure becomes too high for even the most adapted vertebrates. Therefore, at the deepest point of the Challenger Deep, fish are extremely rare or absent altogether, and the ecosystem is represented primarily by invertebrates and microorganisms. Another important adaptation is related to metabolism. At such depths, the metabolic rate is reduced. Organisms live longer, grow more slowly, and reproduce less frequently. This is due to the limited food supply and stable environmental temperature. The absence of light completely alters sensory perception. Vision plays a minimal role. Many organisms navigate using chemical signals or mechanical vibrations in the water. Some species are able to sense the slightest changes in pressure or vibrations caused by the movement of another creature. Bioluminescence, common in the twilight and mid-water zones of the ocean, is less common at the very bottom. However, some organisms retain the ability to emit faint light, likely to attract mates or ward off predators. An interesting phenomenon is the gigantism of some deep-sea invertebrates. Amphipods at extreme depths sometimes reach sizes exceeding those of their relatives at shallower depths. Scientists attribute this to metabolic peculiarities and the absence of certain types of predators. In recent years, genetic studies have shown that many deep-sea organisms differ so significantly from their surface relatives that they may represent separate evolutionary branches. Environmental isolation, pressure, and constant conditions create unique developmental pathways. However, life here does not teem with a diversity of forms. This is not an ecosystem with many competing species. Rather, it is a stable, balanced system where each organism occupies a distinct niche. It's important to understand that the Mariana Trench isn't the only location with a Hadal zone. Similar ecosystems exist in other deep-sea trenches. But it's here that the depth reaches its maximum, and therefore research is primarily focused on this region. Life in the Mariana Trench isn't spectacular. It's not striking in size or brightness, but its very existence is proof that biology can adapt to extreme conditions that until recently were considered incompatible with life. This is what makes the Depression not only a geographical record, but also a scientific laboratory. Despite decades of exploration and several historic dives, the Mariana Trench remains a place we know less about than we might think. Yes, its depth has been measured, its coordinates have been refined, and its main species are known. But when it comes to details, there are still more questions than answers. One of the greatest mysteries concerns the limits of life. We know that microorganisms and invertebrates exist on the seabed, but the absolute limit of vertebrate survival is still not fully understood. Why are fish almost never found below a certain depth? Is this a hard biological limit or simply a consequence of insufficient research? Scientists hypothesize that pressure affects the structure of proteins and membranes so strongly that, at a certain point, vertebrate tissues become unstable. However, theoretical calculations don't always match actual observations. Some experiments suggest that, under certain conditions, organisms could withstand greater pressure than previously thought. The second important issue concerns genetic isolation. The Mariana Trench is a closed system of sorts. Organisms living on its floor don't easily migrate to other parts of the ocean. This raises the question, how isolated are they evolutionarily? Are they distinct lineages or merely adapted versions of more common species? Genetic analyses show that some species of deep-sea amphipods and fishes do indeed differ significantly from their relatives. However, the extent of these differences and their age remain to be determined. The third mystery is the origin of energy. Marine snow is the main source of nutrition at depth, but is it sufficient to maintain a stable ecosystem? Some studies suggest that chemical reactions related to tectonic activity may occur in bottom sediments. If the sediments contain chemical compounds from the Earth's interior, this could provide an additional energy source for microorganisms. It is hypothesized that deep subduction zones may harbor microecosystems based not on organic matter, but on chemical processes similar to those observed at hydrothermal vents. However, direct evidence for this is still lacking. The rate of geological processes is of particular interest. Subduction in the Mariana Trench continues. This means the plate is slowly sinking and the seafloor is changing. But how quickly are the topographic changes occurring? How actively are sediments being redistributed? Due to the complexity of observations, obtaining precise data is difficult. The long-term accumulation of contaminants also remains an open question. The discovery of microplastics was a wake-up call. But how deeply have other chemical compounds penetrated? How do they affect organisms? Research shows that some deep-sea crustaceans accumulate heavy metals and organic pollutants, but the extent of this process is still being studied. There are also physical mysteries. For example, how exactly do water properties change at extreme depths? Pressure affects density, gas solubility, and the rate of chemical reactions. Some parameters are difficult to reproduce in laboratory conditions, so real-world measurements at depth remain particularly valuable. Another question concerns seismic activity. The Mariana Trench region experiences periodic earthquakes. How do they affect deep-sea ecosystems? Can underwater landslides completely alter the structure of the seafloor? Observations show that seafloor sediments are capable of movement, but the precise dynamics of these processes are not fully understood. Scientists are particularly interested in the adaptation of DNA and proteins to extreme pressures. Some studies suggest that deep-sea organisms possess unique molecular stabilization mechanisms. Studying these mechanisms could have implications not only for ocean biology, but also for medicine and biotechnology. The Mariana Trench is also being considered as a model for possible extraterrestrial life. If microorganisms can survive under extreme pressure and without light, this expands the understanding of where life might arise beyond Earth. However, the limits of adaptation remain open. It's important to understand that each expedition provides only a small fragment of the picture. The area of the seafloor is vast, and the number of observations is limited. We can say that we know the general contours of the basin, but not the details. This is precisely what makes it a scientific enigma. Not because fantastical creatures lurk there, but because it is one of the few areas on the planet where fundamental processes, geological, chemical, and biological, interact under extreme conditions. The next section logically focuses on how myths and legends formed around this place, and why people's imaginations continue to fill in the gaps where science treads cautiously. From the very beginning, the Mariana Trench was perceived as more than just a geographic feature. The very existence of a point deeper than any other on the planet inevitably appeals to the imagination. Humans have always treated depth with caution. What lies beneath the surface, especially when inaccessible to observation, easily becomes a source of conjecture. Even in the mid-20th century, when depth data was just beginning to be published, the figures themselves seemed almost unbelievable. Nearly 11 kilometers. It sounded like a measurement error. In 1960, stories began to circulate about supposedly gigantic creatures. Picard's reports mentioned something resembling a flatfish. Scientists later doubted this interpretation, but the story took on a life of its own in popular culture. Articles appeared about fish living 11 kilometers deep, followed by theories about unknown predators. With the development of television and documentary film, the concept of depth became even more enigmatic. Cameras rarely captured a clear image, especially in the early years of research. Any dark spot or distortion in the image could be interpreted as something unusual. The lack of visual data fueled the imagination. In the internet age, the situation has changed, but it hasn't become any calmer. Stories periodically appear online about objects detected by radar, unexplained signals in the deep, and massive forms moving in the basin area. Most of these reports are based on misinterpretations of data or are simply fictitious. Interestingly, the depth itself evokes a sense of mysticism. Humans are unable to descend there without sophisticated technology. Light doesn't penetrate. The pressure there destroys most materials. This combination of isolation and extremity creates a sense of the limits of possibility. Where the accessible ends, the realm of legend begins. Some myths are associated not with creatures, but with anomalies. At various times, rumors have surfaced about strange magnetic readings or unusual sounds. Scientific research has typically found rational explanations: geological features, acoustic effects, tectonic activity. But the myth persisted. There's also a cultural aspect. In various traditions, the ocean was perceived as a place hiding secrets. Even in ancient mythologies, the sea was associated with the unknown. When the existence of a point deeper than which nothing can go became known, this idea naturally integrated into existing archetypes. Cinema also played a role. Science fiction films often depicted the ocean depths as a place where ancient life forms or gigantic creatures might lurk. While screenwriters rarely made direct reference to the Mariana Trench, the idea of extreme depth often served as inspiration. Interestingly, reality remains much calmer. Scientific expeditions have recorded small crustaceans, microorganisms, and rare fish. There are no reports of giant, unknown species. Pressure and limited resources make the existence of large, active predators extremely unlikely. However, myths don't disappear completely. They transform. Sometimes stories emerge about hidden objects or unknown structures on the seabed. Most often, this is the result of limited interpretation of bathymetric maps or poor image quality. It could be said that the Mariana Trench has become a symbol of the unknown, not because supernatural phenomena occur there, but because it is one of the few areas on the planet that humans have rarely visited, and therein lies a paradox. The more we learn about the trench, the more tranquil its image becomes. It ceases to be an abyss in the mystical sense and becomes an object of science. But its depth remains so extreme that the imagination continues to search for something more within it. When a person finds themselves at a depth of almost 11 kilometers, they physically find themselves in a small metal sphere, completely isolated from the surrounding environment. But the sensations begin long before the apparatus touches the bottom. Diving is a gradual transition from the familiar world into a space where landmarks disappear. At first, light and the color of the water are visible through the porthole, with the occasional glimpse of fish. Then everything darkens. The color gradually fades. At a depth of several hundred meters, the blue becomes thick and heavy. Then it dissolves into darkness. At a depth of about 1 kilometer, there are no longer any shades or glare. The floodlights turn on. Their light only illuminates what's a few meters away. Everything else is absolute blackness. This isn't the darkness of night, where there are stars or a moon. This is a complete absence of light. Humans are accustomed to the horizon. Even indoors, there are walls, a ceiling, boundaries. Underwater at great depths, there is no horizon, no visual landmarks. Space seems infinite, not in breadth, but in all directions simultaneously. During the descent, there's a sense of gradually distancing yourself from the surface. With each kilometer, contact with the outside world becomes increasingly tenuous. Radio signals don't penetrate at such depths. Communication is via special acoustic systems, and it's limited. There's a moment when you realize there's more water above you than all the mountains on dry land combined. It doesn't cause panic if you trust your technology, but it creates a profound sense of scale. You're at the furthest point from the sky. Sounds inside the apparatus become especially noticeable. The hum of the pumps, the clicking of the casing, the gentle hum of the systems. Every sound is clearly audible. Outside, there's silence. Water doesn't transmit the sounds we're accustomed to the way we hear them in the air. When the apparatus touches the bottom, movement ceases. Inside, there is almost complete stillness. Spotlights illuminate the silt, which slowly settles after landing. Beyond the light, there is emptiness. People who have been to such depths describe this state as a unique form of isolation. Not fear, but silence. At this moment, it becomes clear how thin the boundary between man and the environment is. Just a few centimeters of metal separate you from pressure that would instantly destroy all life. At the same time, the sense of time changes. Without light and changing lighting, it's hard to feel how many minutes have passed. Everything becomes uniform. The darkness outside the porthole remains the same. Some dive participants reported a strange sense of calm. Perhaps it stems from the realization that there's nothing below. This is the edge of the Earth's surface. Below that, there's only the crust, the mantle, and the planet's interior. There's another feeling too, fragility. People realize how dependent they are on technology. It's impossible to exist here for a second without a device. Unlike in the mountains or deserts, where people can breathe air, the depths leave no chance. Interestingly, fear isn't the dominant emotion. Preparation for a dive takes years. All systems are tested repeatedly. Inside the cabin, there's no sense of immediate danger if everything is functioning properly. Instead, concentration and attention to detail emerge. As the ascent begins, the sensation of movement gradually returns. The instruments show a decrease in depth. The person knows that several hours of return lie ahead. And when a faint blue tint finally appears outside the porthole, a sense of return arises. It's hard to compare this experience to anything else. Astronauts talk about feeling distant from Earth. Diving into the Mariana Trench is feeling distant from the surface. It's the opposite direction, but similar in scale. And perhaps the most powerful impression remains after your return. The realization that there's a place on the planet where you've been, and where almost no one has been before. A place where darkness has endured for millions of years, and where life moves at its own slow pace, beyond human time. At first glance, it might seem like the Mariana Trench is simply an extreme point on the map, interesting for its depth and nothing more. However, in reality, it is part of a complex mechanism that influences the geology, climate, and circulation of matter on Earth. The basin is located in a subduction zone, a place where an oceanic plate subducts beneath another plate. This process plays a key role in tectonics. The Earth's crust is not static, it is constantly being recycled. Older sections of oceanic crust sink into the mantle, where they partially melt and become a source of magma. This magma then forms volcanoes and island arcs. Thus, the Mariana Trench is part of the Earth's crustal renewal system. Without subduction, the planet's surface would have changed differently over time. The continents and oceans look the way they do precisely because of millions of years of plate movement. In addition to its tectonic significance, the basin plays a role in the redistribution of sediments and organic matter. Particles descending from the ocean surface are concentrated in deep basins, making them a kind of carbon trap. Carbon is a key element in the climate system. Some of the carbon bound in organisms settles to the ocean floor after their death. In deep trenches, it can be preserved in sediments over geological time. Thus, trenches participate in the long-term carbon cycle. Subduction also returns some carbon to the Earth's interior. Sediments can descend tens or hundreds of kilometers along with the subducting plate. This is a complex and slow process, but it affects the balance of materials in the mantle and volcanic activity. The trench is also important from an oceanographic perspective. Deep sea zones are linked to global water circulation. Although the main currents occur in the upper layers, cold, dense waters can also move at greater depths. Studying extreme zones helps us understand the overall circulation of the world's oceans. The biological significance is also significant. Organisms living in the Mariana Trench demonstrate the limits of life's adaptation. Studying their molecular mechanisms helps expand our understanding of biochemistry. This could have practical implications for biotechnology and medicine. Furthermore, the trench serves as a natural laboratory for studying the behavior of materials under extreme pressure. Experiments conducted at such depths yield data that is impossible to obtain under normal conditions. There's also a more philosophical aspect. The Mariana Trench is a reminder that much of the planet remains poorly explored. Despite satellites, maps, and technology, the ocean depths still conceal details yet to be discovered. In an era when humanity is actively exploring space, the deepest point on Earth remains a symbol of the planet's inner depths. It demonstrates that even on our own planet, there are spaces that require caution, patience, and precise calculations. The Mariana Trench is not an isolated anomaly. It is part of a living, dynamic Earth system. Geology, chemistry, biology, everything is interconnected here. And perhaps its greatest value is that it helps us see the planet as a whole, not just the surface on which we live, but also the depths that maintain the balance of processes. If you imagine the ocean from the surface, it appears as an endless plain. Waves move, reflect light, and change color depending on the weather. Looking at the horizon, you see only the boundary between water and sky. Everything else is hidden. But beneath this surface, there's a vertical world, and at its very bottom lies the Mariana Trench, nearly 11 kilometers down, a space where there's no light, where the temperature remains constant, where the pressure exceeds 1,000 atmospheres. This place is quiet. There are no turbulent currents, no sudden changes. The silt settles slowly to the bottom. Small organisms move almost imperceptibly. Geological processes continue on a timescale of millions of years. If you mentally trace the path from the surface to the bottom, you can imagine the light gradually fading. First, the blue becomes darker. Then comes the twilight zone. Then, complete darkness. Not a single star, not a single ray of sunlight reaches the deepest point. And yet there is life there. It's neither bright nor loud. It's slow, adaptable, almost imperceptible. It exists outside of human time. Organisms live for years, decades, without knowing the cycle of day and night. The Mariana Trench doesn't appear majestic in the traditional sense. It doesn't offer a panoramic view, doesn't rise above the horizon. Its scale is hidden. It only becomes apparent when you begin to appreciate the vertical. Nearly 11 kilometers of water, a depth through which the bottom cannot be seen from the surface. This is a distance humans have only traveled a few times in history. And there is a special feeling in this. We live on the planet's surface, considering it familiar and well explored. We know the continents, countries, and mountain peaks. But the ocean's depths remind us that the planet remains greater than our experience. The Mariana Trench is the edge of what's accessible downward. Below that, there's no longer any water. Below that, the crust begins, then the mantle, then the Earth's inner layers. This is the farthest point from the sky you can descend while remaining on the planet's surface. Perhaps its significance lies not in record depths or rare dives. Perhaps its significance lies in the sense that it preserves the unknown, not in a frightening way, but in a quiet and steady way. The ocean doesn't seek to be noticed. It simply exists. Its depths don't change under human gaze. The silt continues to settle. The plates continue to slowly move. Microorganisms continue to process organic particles. And somewhere in the deepest point of the Earth, in complete darkness, life continues that has never seen the light. When a person returns to the surface after a dive, the world seems the same. The waves still reflect the sun. The sky remains high. But the knowledge that beneath this surface there exists a space almost 11 kilometers deep alters perception. The planet turns out to be not flat, but deep. Not only horizontal, but also vertical. The Mariana Trench isn't the edge of the world. It's its depth. And perhaps that's why it continues to attract attention. Not as a place of sensation, but as a reminder of the scale of the Earth that we are still only beginning to understand.